Okay. Everybody in Pear Deck, we'll be using Pear Deck for some interactive work, and we'll also be going back to Kahoot, where you can take a look at some of the concepts we'll be talking about today, kind of test yourself to see how familiar you are with that. And I'm going to go ahead and get started. So again, today is software. We'll also be talking about the internet. Throughout our time together, we're going to talk about what an algorithm is, software, machine language, assembly language, high-level language, libraries, packages, frameworks, and then what we mean when we talk about backend versus front end. And we're going to start off, we've got a collection of little interactive things we can do together, but our first topic is algorithm. And an algorithm is essentially a set of rules designed to obtain an expected output from the given input that we provide. So you can see in the flow there, we provide input, the rules interpret that input and automatically provide output. It sounds a lot like our definition of software. Characteristics of an algorithm: it has to have well-defined inputs, and we'll see the importance of this in just a moment. We'll also have well-defined outputs. So we're not going to get sometimes this, sometimes that. We're going to get a well-defined output. There's finiteness. So an algorithm has a start and an end. Has to be feasible, language independent, clear, and unambiguous. In real world terms, an algorithm, you can see here in this tea brewing algorithm, is a set of instructions. And specifically, when we run the tea brewing algorithm, we are instructing, we'll say in this case, a person to put a tea bag in a cup, fill a kettle with water, boil the water in the kettle. And you'll see the distinction there that we have boil the water in the kettle, pour some of the boiled water into the cup, add milk to the cup, add sugar to the cup, stir the tea, drink the tea. Sounds pretty simple. Algorithms can be designed to run in sequence. So we have an order when one step ends, the next step begins. We have the option of setting it up to branch. So one set of instructions executes. Got a question about algorithms. Let me go back to that in a second. So branching with an algorithm. So you can have a different set of instructions execute depending on whether something evaluates to true or false, yes or no. And you can see when we come into our decision point, so we've got an instruction coming into the decision point here. If the answer to, say, that question is true, then the algorithm moves into a set of instructions you can see here represented by the rectangle on the right. If that instruction qualifies as false, then we're routed into a different set of instructions. Ultimately, whatever takes place in those instructions, this particular design is showing us we then are routed back to a, say, conclusion point in that segment of the algorithm and move on through the rest of the algorithm. We also have looping. So we're going to retry a set of instructions multiple times. And a lot of times with looping, there is some sort of limit to the number of times something can loop. We'll see that. So the instructions come in this example to our decision point. If that decision point evaluates as false, we move on in our instructions. But if that decision point, whatever it's evaluating, is true, then we move into another step. That step is completed, and then we are routed right back to our decision point, essentially asking, is this true or false? And if every time it evaluates as true, it's going to execute this batch of instructions until we get to a point where we no longer produce a true result. And then at that point, we continue on with the rest of the code in the algorithm. Just going to go back to our slide. And so this is what you were wondering about. What does finiteness mean? And finiteness is just a way of saying there is a beginning and an end to it. So algorithms don't go on forever, ever, because we have a result, right? At some point, that algorithm ends its evaluation and provides us with a result. If you watch The Big Bang Theory, you are probably familiar with Sheldon Cooper, PhD, and Sheldon has created a friendship algorithm. And so we'll go through the friendship algorithm together to kind of see how Sheldon evaluates whether or not a friendship has begun. So Sheldon places a phone call. He moves into the decision point, is the person home? Yes or no? If the person is home, he moves into this portion of the algorithm. If the person is not home, he leaves a message, he waits for a call back. So if he's waiting for a call back, he is routed, if you see, all the way back to the point where he's able to talk to the person. So he waits for a call back. Once he gets that call back, he moves into this step. So he's placed the phone call, they're home. So if they are home, he moves into this step quickly. All right, once he gets to talk to them, he says, would you like to share a meal? And then there's another decision point, yes or no. If the person says yes, they go ahead, they dine together, and they move straight into beginning their friendship. But if the person says, no, I do not want to share a meal, then he moves into, do you enjoy a hot beverage? And if they say yes, then he moves into an evaluation of, is it tea? Is it coffee? Is it cocoa? He also has to evaluate, does he have, or he also then moves out in, if they select tea, then they have tea. If they select coffee, then they have coffee together. If they select cocoa, then they have cocoa together. Once that takes place, they move into beginning their friendship. But if we come back up here and they do not enjoy a hot beverage, then he routes all the way back to here and he evaluates for n. And if n equals no, so we move into the next step. So he's setting here n equal to no. He hasn't asked this question at all, but he has, we'll see, set up a loop that he's going to ask this question multiple times. So the question is recreational activity. Tell me one of your interests. And then we move into that decision tree. Do I share that interest? Yes or no? So if it's yes, let's do that together. Why don't we do that together? And then they partake in the activity. They move immediately into friendship. But if they do not share an interest in that activity, Sheldon moves into this counter. So we've set our counter at 0. He moves into this counter and he says, okay, well, this is the first iteration of me going back and asking that question again, because I don't share that interest. I'm going to see if there's another interest. So the first time I asked the question, I set n equal to 1. So since n is 0, now n is 1. It says, okay, well, is n greater than 6 yet? No. So we can go through and we can ask for another activity that they like. Now, if n is greater than 6, what Sheldon does is he chooses the least offensive interest, thing that he can tolerate doing. They partake in the interest and they begin their friendship. But if like in this case where n equals 1, he goes through and he probes again. All right, give me one activity that you find interesting. And he evaluates that. Do I find that interesting? No. So then now n has been 1. We add 1 to n and we get 2. That is still less than 6 times. He goes through that loop until we get to his 5th time asking that question. We add, or 6th time, we add 1 to 6. We go up here and we evaluate now. N is actually greater than 6. He's asked for 6 different activities. He's out of luck. He doesn't like any of them. So he has to choose the least objectionable interest. He moves into partaking in the activity, and then thus they begin friendship. So a couple of different things happening there, but essentially that is kind of how we establish friendship. It's by doing activities, but he actually has a very nice left brain analytical way of evaluating friendship. Okay, essentially algorithms evaluate instruction. That instruction can be in the form of sequential instructions. That instruction can branch. You can see here we have an evaluation of whether something is true or false. In this particular example, we have a few places where in this particular algorithm, we have to determine if something is true or false. So in this case, he's placing a phone call. Is the person home? Meaning, do they answer it yes or no? Depending on how it evaluates, that's going to put us in one of 2 directions in terms of instructions. So something evaluates to no, then we boom, 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 we follow these instructions. If something evaluates to yes or true, we boom, 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 move into another set of instructions. Another thing we can do, we can design an algorithm to do is loop. So in this case, we go directly into a decision point and we have to evaluate if something is, again, true or false. If something is true, we then perform a loop. And so in this particular example, we are evaluating if one person shares an interest with another person. And if that person does not share that interest, in this case, this is where we go through the loop and we are interrogating whether or not an interest exists that both people find interesting. So if someone says, I like to go for a walk in the park, then in Sheldon's example, then they go ahead and they do that together. But if Sheldon doesn't like taking walks in the park, then he loops back around. He says, all right, give me one more example of something you like to do. And every time he doesn't like doing that, he counts and adds 1 to the number of times he's asked that question. So here we're establishing that in this case, this value n, or the number of times he's asked the question, is 0. He asks the question, now he adds a 1 to 0. He goes through, it says, all right, have you asked this 6 times already? If no, ask it again. Once he's asked this 6 times, if he still doesn't find something that he likes to do, he moves into another decision point. So that's the illustration of how we can design algorithms to operate. So that's how that's related. All right, we also have something in algorithm development called pseudocode. And pseudocode is a method of describing actions in a way that we can understand. Obviously, when you get into actually coding the algorithm, you are using full-fledged code that may or may not make sense to talk it out. But we use pseudocode in the design phase, so we can get an idea while we're developing, maybe with other people, what we're trying to do. And the pseudocode is similar to how I explained the algorithms. So here, pseudocode, we're setting a total to 0. So that is how we would write out in our design something like this, setting a total to 0. get a list of numbers. So go out and fetch from the system a list of numbers. Another example, loop through each number in the list, add each number to total, end a loop. So this is a way that we would describe this section where we're going out, we're getting a number, and then we add the totals for each number in the list. If a number more than 0, print it's positive, message else, print it's 0 or less, message end if. And so this is conditional, where it goes out and evaluates if the number is positive. And if it evaluates that a number is positive, the instruction that we're going to need to develop is, okay, we need it to print out it's positive. If the number is not more than 0, then we need to code this algorithm to print it's 0 or less. Once we get an output, either it's positive or it's 0 or less, we end this evaluation and we move into the next step of the algorithm. So pseudocode is an artificial and informal language that helps programmers develop algorithms. Pseudocode is text-based detail in design. So now I want you to go ahead and I want you to write out, based on what we talked about, what is an algorithm? What is pseudocode? So go ahead and give me your interpretation. Type that out for me and we'll check it out. Okay, let's go through some of these responses. So algorithm, set of clear, concise instructions. Absolutely. Sequence of steps to get an outcome. Yes. Specific directions. Yes. A flow chart of certain activity. An algorithm, in that flow chart, we actually, in the terms of software, we then code that into actual software or code instructions. So yeah, to actually plan out your algorithm, we create flow charts, especially if we're working with end users, to ask them and confirm that we understand what they're trying to tell us. And that's also where in software development it can get tricky, is how we interpret the requests or the needs of the person that's asking us to develop something. All right. Algorithm is a list of getting result. Yep. A set of rules to be followed while you solve the program. Set of instructions. Pseudocode is a normal language. Right. Pseudocode is easy for us. It's informal. It's easy for us to understand when we're discussing with someone else, or we're recording what someone is telling us they need the algorithm to do. Algorithm is a route from start to end. Basic route plan. Algorithm, sequence of rules to achieve the results in the end. Pseudocode, artificial language to create an algorithm. Algorithm, set of instructions. These are excellent. So instead of going through all of them, because I think based on the answers, you guys you're okay with this concept. Thank you for that. All right, we are nearing the break time. So I will just go through this comparison and then we will take a break. All right, so algorithms versus pseudocode, really just a nice table to show us that algorithms are unambiguous, very specific instructions of how to solve a problem. Whereas the pseudocode, often used when we develop the algorithm or a way of us communicating to others what the algorithm does, especially if somebody doesn't read the code. It also is a fast way for us to record while we're developing what an algorithm has to do, because sitting and coding that does take a lot of concentration and thought, where the pseudocode allows us to just jot down the logic quickly. So pseudocode, informal, high-level description of the operating principle of a computer program or other algorithm. The algorithm helps to simplify and understand the problem, where a pseudocode is a method of developing an algorithm. When we return from our break, we will get into what is software. So go ahead, take a break, meet me back here at 11 a.m. Eastern, so 15 minutes from now, and we will move on. Talk to you in a sec. the whole point of us talking about algorithms and going into the detail of algorithms is because that's the building blocks of software, of coding. And you guys are going to be experiencing that throughout your time with us at Clarusway. So let's talk about software, how we define that. It is unlike hardware in that it cannot be physically touched. It is the missing link between the computer hardware and the data that the computer hardware is processing. It has to be loaded into the computer's RAM before it can be run. Remember that RAM is that random access memory, or that temporary memory that the CPU utilizes to actually compute instructions from the computer. It's a set of pre-written instructions which the computer executes in order to perform a particular task. And it's typically written using programming languages such as C, C++, BASIC, Java. You guys, there's a number of languages that can be used. When we look at the architecture of how software interacts with hardware, we have at the base our hardware. So the processor, hard drives, RAM here, our keyboards, mouse, monitor. And then we move into system software. And that system software is what is interpreting what's up top here and allowing the computer's hardware to interact with one another. So that's divided into a few categories here. You can see that system software includes operating systems. It includes device drivers. It also includes utilities, something like your antivirus software or your disk cleanup. And your device drivers, you can see here, it has I/O, and that's your input-output interpretations for your different pieces of hardware here. Application software, you're using application software right now to actually join us, whether you're using Zoom or Chrome, any of those browsers. When you go into Gmail, if you use Gmail to check your mail, that's all application software. All right, so go ahead and give me an answer here. Have you heard of any programming languages? I just mentioned a few, but have you heard of that term? Have you heard of programming languages or of a particular programming language before? Go ahead and let me know. Show me your dots. We have a lot of folks who have heard of programming languages. If you haven't, then we will be talking about some of those. And so by the end of class, you will be able to say, yes, it's true, I have. Software has different components, different types of software. So we talked about the different architecture of a computer, where we have our hardware, our system software, and our application software. Let's talk about the code, the language that is used in software. So our base layer here is our hardware. We use machine language, which is software, to actually work with our other languages and the hardware. We use assembly language to interact our high-level language with machine language, so it acts as an interpretation. And then we have our high-level languages, and so examples of those: Python, C++, C, Java. So the middleware between the zeros and ones that we talked about in the last class and the high-level languages are these, our assembly languages, our machine languages. So more specifically, our machine language here, that is the binary that we discussed the other night. And then the assembly language actually is our interpreter there. So assembly language and machine language are considered low-level languages. So you can see we have high-level language here. These two guys are grouped into what is considered low-level language. High-level languages, again, you've got the languages we've talked about: C, Java, C++, Python, JavaScript, Rust, Golang. JavaScript, you see that often in web page design. Sometimes when you get issues with visiting a web page, you may get an error message that indicates that you had a script issue on the page. The differences between high-level language and low-level language is high-level language is interpreted, whereas low-level language utilizes direct memory management. And so our direct memory management is a more efficient use of memory. In some cases, it's memory that is integrated with the CPU or set aside outside of the CPU to become a more efficient memory component. And now when we talk about that, we're talking about very basic coding, allowing us for the hardware components to interact. It kind of just has limited instructions there, where a high-level language is going to give us a lot more flexibility in terms of what our a lot more flexibility in our instructions. We're going to be able to do a lot more, whereas low-level language, it's very simplistic statements. High-level language uses something called open classes and message style methods, which are known as dynamic constructs, whereas hardware has very little abstraction, none, in that again, very simple instructions, very basic instructions. High-level language can cause poor performance, where our simplified low-level language really has minimal impacts on performance. In high-level language, codes are concise, and then in our low-level language, statements correspond to directly to clock cycles. And when we talk about clock cycles, we're really talking about how the CPU processes instruction. So clock cycles specifically is a cycle or a single electronic pulse of a CPU. Since modern processors can complete millions of clock cycles every second, processor speeds are often measured in megahertz or gigahertz, and that's the frequency of the processor. And it's also known, you'll hear it referred to as clock speed. And sometimes when, at least in the past, you can configure clock speed of a processor. And in the past, you would hear folks of overclocking their processor. So they would speed up the rate at which the processor processed data instructions. But that usually resulted, if you weren't careful, in you burning out your processor. So we talked about how that piece of hardware, that processor, is very hot. It's processing electrical signals. And we also have that special heat sink on top and a fan that then blows on that heat sink. So overclocking is not necessarily healthy. So high-level language, flexible syntax, easy to read. But again, low-level language, just like binary, is not easy to read. It's not easy to write. So low-level language, superb performance, but difficult to write. High-level language is object-oriented and functional. When we say object-oriented, we mean that you can interact with objects on a screen. So when you are coding for a web page, your objects on the screen, your fields, your images, that's what you can code for and interact with. Whereas your low-level language, it is not fancy. It does not do anything, visually impactable. And then low-level languages are very difficult and hard to learn, and so not much support out there for them. And when we talk about high-level language, there is a large community out there using those high-level language. Lots of Java programmers, lots of C++ programmers out there. right, so go ahead and give me your own interpretation of what high level versus low level means to you. All right, some responses. High level language is easy for a programmer. It represents the proper software out there that we think of, and it's high level is understandable. Low is complex, difficult to write. Again, high level, easily used, easy to program, easier to read, and easy for humans to understand. Whereas low level, really, your computer understands that. Only your computer understands that, unless you spend a lot of time writing low level language. High level is easy to learn, understand, and visually appealing. These are all correct. So I've got a request to see an example of both types of high level and low level, and we will. We'll take a look at that. The first example is machine language. So when we go back to our pyramid, our machine language is actually our intermediary between assembly language and hardware, where our assembly language is that intermediary language that interprets high-level language and our machine language. If we go back and we look at machine language, this is what is interacting with our hardware. So this is our binary, our old friend binary. And when we write out z equals x plus y semicolon 2 in binary, in that machine language, this is actually the code for that. So that's just a fragment of code out of lines and lines and lines of code. Assembly language is actually converted to machine code. And you can see in the example here, we have a very limited set of instructions or keywords that we use in assembly language. And this is a calculation of sorts. So assembly language uses mnemonic to represent each of the machine language commands, and sometimes abbreviated also as ASM. So you may see assembly language called ASM. It functions to do basic operations like addition, subtraction. It uses short descriptive words that you can see on the screen there. So move, sub, move, add, move, compile, or compare rather. The assembly language is converted into executable machine code by a utility program referred to as an assembler. So we write out what you see on the screen, that assembler interprets it, and then it converts it into the binary that we saw on the previous slide. So what we can see here in our example, we see an instruction to move. Two values are represented here. So in this particular instruction, we are telling the computer to move something located here to something located here. In this instruction, we're commanding the machine to subtract something. So subtract this from this. And again, not easy to read, obviously. Again, moving the value that we subtracted, adding something to the value that we moved, 2 commands to move, and then we have a compare command here. And there's also a command jump, which allows us to, when we provide that instruction, we'll say jump to another line. So that is also like a loop where we get to that jump line of instruction and we say, okay, move back up to this step and do it all again. Here is another example of our assembly language moving through the assembler into machine code. So what you see here on the left-hand side passes through the assembler, which converts it to our machine code here. High-level languages. Again, examples of high-level language, live code, Ruby, PHP. A lot of web development takes place in PHP. Source code. You can see there is an example on the right of code, source code, and high-level language. So that is a good snapshot of high-level language. So you can see some of the words there. Function, window. These are words that you've heard of in the English language. So rather than having something like this, it's not words. It's not easy to read. It doesn't make sense to us in terms of when we think of language. When you look at this, there are references. You know the term with, right? You know the term if, else. All right, let me look at the questions coming into Zoom. Who are the geniuses who write machine languages? I don't know anybody that writes machine language. I have a question. Which one is the machine language, left, right, or both? Is that from this slide that you're wondering? Is left or right? That whole thing is considered assembly language. It's a combination of commands and parameters. So when we say move something, we have to tell it what to move. And I have a question also. Is assembly language the same thing as IDE? And an IDE is actually an integrated development environment. And so it's a software for building applications that combines common developer tools into a single graphical user interface. And so that really is an environment to develop using higher level language when we think of IDE. So source code, when you hear the term source code, again, it's that human readable text written in a specific programming language. To the right here, that looks like Java. I'm not 100% sure if that is Java or something related to it, but it's scripting language is what you see on the right. All right, when we talk about code, we often, in combination with source code, we use a compiler. And what that compiler does is it takes our source code. In this case, this is a code in a file hello.c. And it compiles that code, that set of instructions, into what the machine, the hardware, the processor, what all of that can understand. So it compiles our readable code into that unreadable code, that machine code. Or we also refer to machine code as a binary executable. And then we run the machine code and we get the result. So in our source code, we've coded this to print out the word hello. It goes through the compiler, converted into machine code. We run the program, we get the result that we developed for, which is hello on the screen there. And another thing we see called, similar to the compiler, is an interpreter. And so in this particular example, we also have code. Now, if you see here .c and .py, these are two different languages. So this is C, this is Python. And so depending on the language you are using, you will see different technologies, different methods of achieving the same result. So our Python goes through an interpreter, to produce the result that we're looking for. We talked about especially in our Kahoot and the other evening, we talked about open source software, free software. Essentially, you have two components where you just have free software, and then you have open source where people are able to go in and take that software and help develop it, that sort of thing. There are derivatives that come out of that open source, but free software, essentially, you can use it any way you want. And you can see the two large contributors to that. Both of those efforts are Richard Stallman and Linus Torvalds. These guys were integral in creating these two mechanisms for sharing software. And essentially, we have different approaches to what the mindset was of someone that was interested in free software versus someone that was interested in open source. So free software, they wanted the freedom to develop software and have an ethical approach to developing software. Obviously, there is there's different ethics involved in software development. Obviously, you want to develop software that is in the best interest of the user. It doesn't have any exploits where you can use that software to cause harm. And then on the open source side, that's more of a technical purist approach towards quality, right? We all want to contribute to this collection of software so that we can create the most optimal software that we can. And the other side of, or the other end of the spectrum, is that privatized software, where that software is not shared and it's for profit, but there's this wall of confidentiality. So other folks out there aren't able to take that software and enhance it unless you work for the company that develops that software. So then on the right here, we had the bug found in the hardware. So I have to point out that this detail of logging is very impressive. Obviously, with software development, you take and you record, you log, you take notes of what you're developing. You also comment within the code exactly what that code segment was designed to do. But this is really impressive that they put the moth in the logbook. So kudos. Let's take a look at bugs, right? Bugs can be displayed a couple of different ways. There's the hardware method of a bug where you're communicating with hardware and there's an error and the hardware does not run anymore. And then there are bugs with software. And bugs are simply just a mistaken way of coding. And so what we see on the screen here is the syntax to a line of code. And the proper syntax for this particular line of code, so the result that we want to see with this line of code is we want to print to the screen, similar to what we saw in the examples with the hello. We want to print to the screen, Clarusway rocks. So we want that to display on our monitor. In order to achieve that result, we use the keyword print. We enclose in parentheses some value that we want to print. Now, in this example, we have the string, a collection of characters, Clarusway rocks. And so we've offset that string with these quotes, double quotes. We could ask the computer to print out numbers, and numbers don't require quotes. So that's why you see these quotes here. But taking this combination of syntax where we have to have the word print, we have to have our double parentheses, and we have to have our double quotes. Where we open something, we must close it. So We open the parentheses, we need to see close. We open the quote, we need to see the close. So the next slide, when you take a look at these instructions, based on what we saw, and I see somebody placed that syntax in Slack as well. When you take a look at these 3 sets of instructions, real quick, give it a look over, because we're going to go through and we're going to talk about what the issue is in each one of these lines of code. So this one will let you write out the corrections if you see the issue. We'll also talk it through. Okay, so let's take a look at the bugs on the screen. Print, open parens, you can see towards the end there, that's where our bug takes place. That's where the error takes place. So we have print some number, comma, some number, but we do not have for our open parens, we do not have the corresponding closed parens. So where you see the yellow there, that's exactly right, that's perfect. That is where our bug is found. So when the machine, when our compiler is reading that instruction, if we don't have that closed parentheses, we haven't told the machine what to do properly. It's going to get confused, and you're not going to see the result that you are planning for. In the second example, we have an error here in the keyword phrase. We give the computer a library of keywords that we program it to understand. We have not given this particular computer a definition for PRNT. We've only defined what print is. So when we don't code the proper keyword, or the function name is what this is also referred to as, then of course the computer, we get an error. It doesn't work. Okay, third example, where you see this black highlight, that is actually the start of the error. So we've got the right keyword, we've got our open parens, we've got our closed parens, we've got an open quote, double quote, but we do not have the terminating double quote. So whenever we open parentheses, we have to close them. Whenever we begin with a double quote, we have to, at the end of the string that we're trying to, in this case, print out, we have to terminate that with a double quote. And so those are, in this particular set of instruction, those are the different issues, because we saw we have to have the word print. That is our function or our keyword. We have an open parens, closed parens. We have a double quote situation around our string. And one thing that you see here in these instructions is a semicolon. And typically in programming, when you instruct the computer with a function, those functions usually end with a semicolon to instruct the computer to move on to the next instruction. So when you see semicolon, that essentially is telling the computer, all right, that was everything that you needed to know. Now execute that instruction. So by the time we get to semicolon, if we got all of this stuff before the semicolon accurately written out, then it knows that that is the end of the instruction and it can execute. So you do see semicolons in languages that you will be working with. Libraries, packages, frameworks. So the print function. How does the software, the computer, know what the print function even means? So in high-level languages, we have these keywords or these functions, and we define what each one of these functions can do. And then we combine all of these functions into packages that essentially are a library or a collection of pre-written code. And so software libraries generally consist of pre-written code, classes, procedures, scripts, configuration data, as well as other terminology. And a developer might manually add to a software library for a program to achieve more functionality or to automate a process without writing code for it. So if you have a particular set of instructions that you want to define, then you can add that to the library. And when you are coding through your high-level coding, you can just call that set of instructions by using a keyword or a function name. When we talk about functions, so functions are typically that basic combination of instructions. We saw print as our example. You combine or collect functions and group them into what is called a module. And so a module is just a collection of a bunch of different functions. And the functions typically in a module are related to each other, right? You don't see a function for printing, a function for displaying to screen, and then a function to do something completely unrelated to output, right? In this particular example, we actually see how to write out returning a square, a number squared, right? And in this particular set of instructions, we are defining a square of x. And so when we call square, the function square, what we were actually looking for the computer to return is whatever number we put here in the x position, we want to see that x multiplied by x. So when we say print, because we've already got that function that we've defined in the library for print, we don't have to code out exactly in our coding here what printing means. We call the function square. We say square the number 4. And then what we see in our output is 4 times 4, which is 16. So in the code, we're defining square of some number, which is coded to return our number times our number. Then we call the function of print what's in the open parens, end parens, which is the square of 4. And also, just a note, you can see that we've nested a function within essentially a function. So we're printing now not just a string of characters, but we're printing out the result of a calculation. I'm going to take a break here. We've got, we're at 11:46. I'm going to ask you guys to come back at 12:01, so you guys can have full 15 minutes. So 12:01 p.m. Eastern. And I've got a question. Where is this writing taking place? And when you see this writing, when you see coding, actually each of your languages, you're going to have a tool that is set up to not only allow you to write your code, but then compile your code. And I use a tool called SQL Developer to actually code in SQL and procedural language of SQL. All right, so break. Now, come back at 12:02. So I've taken up 1 more minute of your time. 12:02 p.m. I will see you then. So looking at the screen, we were talking about libraries, packages, functions, and we talked about a module, which was a collection of functions. And so here on screen, we have a collection of functions. We have the function square, and we also have the function print, which we told it to print whatever the result of the function was. We had a question earlier about IDEs, and we had a question now about where's the writing taking place on the screen? Where would you write this? You just write this in a Word document? No, you actually write this in an IDE, or an integrated development environment. An integrated development environment is essentially a framework that comes with, or a collection of software that is designed to help you develop for a specific technology. If you look at my screen here, this is what I use. It's called SQL Developer, and it is software specifically developed so that I can develop for Oracle databases. Oracle being a company that is known for their database technology. Another common IDE or environment like this that you see here is Visual Basic Editor, and that is known as, Visual Studio, and that is a source code editor that runs on Windows, Mac OS, and Linux. So your big, most popular operating systems, so that you can code. And it is top pick for JavaScript and web developers. So it allows you to code in those two languages. And it knows how to compile that code into the machine code that the assembly code, machine code that we need to actually run our computer. All right. So we talked about our functions comprising, multiple functions comprising a module. When we have multiple modules, then we collect those into what's called a package. And when we collect multiple packages, we can actually term that a library of code. And libraries of code, you can see on the right here, there are some examples. So our framework, our IDEs, is software that is developed and used by developers to build applications. So you can see there are some of our frameworks that you can code with. You see ASP.NET a lot for web development. Here are different frameworks for different types of development. You have frameworks for web application framework. You have mobile development framework, a data science framework. So each one of these frameworks is really developed and organized to help you do very specific type of development, where data science, data mining, that framework is going to be much different than a framework for you to develop a web application. And you can see here are items within the PHP framework, that web development framework. Again, more frameworks for web development, Django and Flask. You may hear those referred to. Backend and front end. Essentially, this is an illustration to describe what we mean when we say this is front end code, or this is a front end component versus a back end component. And the back end, you can see, is actually, there's a lot going on there, a lot of different things happening. Can be kind of messy, a collection of so many different components. And then what you see on the front end is what the user sees. So really nice, neat, welcome presentation. Whereas on the back end, if we showed the end user, the person, say, using a web page, all of this stuff, it would be overwhelming. Here's another example. So our users, what they see is that front end, that nicely small, nicely tailored, smaller component, and then all of the business that you need to actually produce that front end component, that's known as the back end. That's your databases, that's your code, that's your technologies behind the scenes. And yes, I think that one on the left is a real lion. I think that's Photoshop. All right, so differences between front and back end. Front end refers to the client side of the application. So if you hear the term client side, that is user facing. Back end refers to the server side of the application. Front end, it is the part of the website users can see and interact with, and then the back end is everything that happens behind the scenes. A front end typically includes everything that attributes to the visual aspect of a website, or not only a website, but if it's a piece of software. In the back end, it generally includes a web server for a website that communicates with a database to serve requests that the front end presents. So through the front end, the user is going to enter a piece of information that is going to be stored in a database in the back end. In the front end, it forms the basis of what users can touch and experience in their web browsers, where the back end, it has all the brains of that experience, and it is never visible to end users. Front end, you may see technical terms associated with front end, or like HTML pages. The CSS or the style sheet for a web page is what prevents that unified formatting, and JavaScripting. That all is used to create the front end experience. And then the back end of that experience, you'll use software development code and tools for Ruby, Python, Java, .NET. So those are some of the back end technologies related to web development. All right, so out of everything that we learned about software, go ahead and jot down some thoughts on what you think is the most important thing you learned from the software topic. What are you going to walk away never forgetting? And don't say the back end of a lion, because that is not a valid response. All right, very specific instructions are necessary for an algorithm. That's awesome. It's not physical. I can't touch it. The lion is what you're going to walk away with. Software's connection between the hardware and what people see. High level versus low level software. That's a great one to take away. Within what you see and that hardware that you actually buy from the store, there is high level software, low level software. That software consists of libraries. A library is a collection of different algorithms. That's exactly true. All right, I love it. Great responses. Okay, let's talk about the internet as we close out our class. We're going to talk about everything internet, all the components that allow us to utilize the internet, all of the back-end details, if you will, of the internet. We're going to talk about that internet term, what it means. We're going to talk about TCP/IP protocol, DNS, LAN, and WAN, and I'll tell you what all these acronyms stand for as we go through this. All right, the internet. The internet is essentially a network of networks. Let's see. So whether it's a laptop or a server, all of these different computers are connected together through a network, through networks of networks. The birth of the internet was essentially driven to develop a common repository for information, ideas. You can see that we've got on the left here, we've got mathematicians, scientists calculating things, and ultimately we wanted to be able to organize this effort so that we could collectively work on projects. You can see on the right, the result of one of those projects was the space effort, trying to get folks to outer space and to the moon. So it was a way to collect common sense details, information. We saw in our first Kahoot the term ARPANET, and that actually stands for the Advanced Research Projects Agency Network. And it was an experimental computer network that was basically the forerunner of the internet. And the ARPA, Advanced Research Projects Agency, an arm of the US Defense Department, funded the development of ARPANET in the late 1960s. And its initial purpose was to link computers at Pentagon-funded research institutions over telephone lines. And really, even though it was the Defense Department, which you think in terms of military, if you look at all of the sites that were included in that network, they were academic. So you can see how the internet really was picked up and utilized by academic institutions. And that was the first place that I was ever exposed to the internet. It was a way to combine library systems. We saw the term distributed in our Kahoot. And here's a graphical representation of 3 different types of topologies. We have a centralized topology, a hub and spoke centralized, where you have a common connection point, and then you have all these spokes out to different, that terminate in different areas. This is a hub and spoke, essentially decentralized, where you have a multiple combination of hubs and spokes. So you have centralization points, but then each one of those centralized topologies combine to perform to create a decentralized network, right? And then distributed. There's no common point for these. And that is essentially what the internet is there's really, you're not connecting all the time to a specific website, right? You can go all over, you can go to servers all over, so distributed. Here's a timeline of where your common internet related tools were developed. You see ARPANET is way down here at the beginning of the timeline. And then you can see common things that we use today: eBay, mid-90s, Yahoo, Amazon.com, mid-90s. Google was a little later, almost to the year 2000. Facebook here, 2004, YouTube, 2005. And we've been using these things for quite a while now. TCP/IP protocol. So we saw in the Kahoot, IP stands for Internet Protocol. TCP is Transmission Control Protocol. So we control the protocol for Internet Protocol. And you will see that term TCP/IP used often in Internet technology. Essentially what it is, it's rules for sending information between computers. It is a protocol followed by both the client side and the servers used in that communication. And you can see in the picture there, what is actually happening is this computer is calling out to the server is acknowledging that call out, and then once that server acknowledges the client acknowledges the server. And to talk a little bit more about that, you want to learn the term for that 3-way connection. And that's it's called the 3 handshake, right? You've got the synchronized request to the server, 1 handshake, the synchronization and the acknowledgement of the server back to the client computer, and then the acknowledgement back to the server. So you know, it's kind of when you cross the road, you look left, right, and left. Essentially, you're reaching out, getting acknowledgement, and then reaching back to actually submit your request so that you can start utilizing that machine. HTTP, if you look at your URLs, your web addresses, you're going to see them start with a acronym HTTP, and that's a hypertext transfer protocol. And that is a request response type of protocol that's set up when we go to a website, we request information from that website. And when we see the page render for that website, that is the response to our request. So that is our 3-way handshake. IP, our Internet Protocol, is essentially a collection of numbers known as an IP address. You can see here, it's a decimal. It's a combination of numbers separated out by decimals. When we learned binary, we learned that each one of those binary numbers was assigned a I'm sorry. Yes, I don't want to confuse you, but each one of those binaries, it represented a base 10 number, right? A decimal system number. And so for each one of these binary combinations, these are the numbers. And so when we are talking about an IP address, it is a combination of these numbers that identifies your computer or where you're making the request from. It is a combination of 8 bits, 4 segments of 8 bits, a total of 32 bits or 4 bytes. And so when you see IP in this 4 bytes combination, it's known as IPv4. Essentially, your IP address is similar to a letter, writing a letter, right? You have the address that a request is coming from, and a request or an address where the request is going to. So your computer has an IP address, and the server where we're making that three-way handshake has an IP address. In terms of computer information, this is essentially what the computer sees. So we see that combination of 4 numbers for your computer, and that combination of 4 numbers for the server side. There's also something known as IPv6. The IPv6 address, it is 128-bit, and now it essentially is our numbers, our 4 numbers, but now instead of 4 segments, we have 8. I want to show you. This is a PC, and this is the command prompt on a PC. So it allows me to interact through a text-based format with my computer. And if I want to see my IP configuration for my machine, at that command prompt, I can type in ipconfig, and you can see that it brings back all of the network-related information on my machine. And specifically, I want to show you here, this is where I can find my IPv6 address, and here is where I can find my IPv4 address. So just not necessary to learn that right now, but just want to show you where that sort of information is used on your machine. Private and public addresses. A public IP address, so what you see on the right, it identifies you to the wider internet so that all of the information you're searching for can find you. But behind a public IP address, if you are on a network or you are using a router, you often have what's known as a private IP address. And so that is used within your private network, the smaller network that you're using to connect securely to other devices within the same network. And you see this a lot in business, where businesses allow you to work on their internal network. And then when you execute a request to a web page from within your business's network, it actually submits that request to the greater internet using a public IP address. And there's hardware in between your computer and the internet that knows how to convert what your private IP is requesting to this public IP address. And then conversely, when that response is received, where to send that response back to your private address. In order to make that translation, we need technology known as a NAT, or a network address translation. And so your host, your computer that you're using on a private network, is routed through a router that uses NAT to translate what your address is into a public address here. That's the public address that we're finally sending to the internet, some server on the internet. And then when it returns the response from the internet, from the server, it goes back through that router that uses that translation back to your machine. So here's a little explanation of how the different values are handled. This is your private IP, 10.0.0.1. This is your public IP, 150.150.01. And then this is the IP or the address of the server. DHCP, what do we mean when we talk about DHCP? DHCP stands for Dynamic Host Configuration Protocol, and it's a client-server protocol, right? Protocol, when we say that, it's a collection of rules and procedures that automatically provides an IP host with its IP address and other related information, such as the subnet mask and default gateway that a computer should use on an internet or on a network. So in this case, what happens is when your computer starts up, you have this dynamic process that says, okay, the IP of your computer is going to be ... So whatever that combination of numbers is. And then that identification goes through that process of connecting to the router and out to the internet. The way your computer actually gets assigned that IP is your computer goes through that router, which accesses the DHCP server, which kind of has all of those combinations of IPs that are permitted in your particular network, picks one of those IPs and says, okay, computer, this is your address. You can have a dynamic way of assigning IPs. There's also something that allows you to assign IPs in a static fashion. So your IP isn't changing every time you try to connect to the internet. But the technology that provides that assignment is known as DHCP. How information is transferred over the internet, we refer to that in terms of packages. And so packages are essentially a collection of information in your network transmission. And a building block of that package is called a packet. And packets are transmitted over networks. Let me show you a little more. So packages are packets of information. Your computer here needs to transfer information over to computer 2, or say a server. It is transmitting that data in a package. A package is a collection of packets. And you can see that here, we can see that this particular package has packets of information, 1, 2, 3, 4. Packets do not need to be sent in the order in which they were put together. So when you have a message that you're sending across the internet, you have that package of information. You have your routers, your technology in between your computer and the server that is breaking down those packages into packets. So that transmission that you're making is faster. It doesn't have to transmit the whole package of data. It breaks it down into smaller packets and transmits them all over. You can see we've got packet 1 here arriving at our destination, our server or the other computer, last in the order that these packages are, or these packets are received. Let's see, got packet 4 down here. That may not take as long as packet 1, and so that actually arrives at the destination server computer first. So your computer has technology that breaks that large package into smaller packets, and then at the destination computer, that has technology that knows all right, well, I've got all these packets that are part of the same package. Now I have to order them in the order that they should be in and combine them to create that entire package of information and provide that information to whatever the server or the user that needs that information. So your message, when you send information over the internet, your message is broken down into smaller packets, which are labeled, and they are identified in terms of where they are organized in terms of that package. They travel independently over the network, perhaps arriving at their destination out of order, and then they're compiled in the correct order to obtain what the original message was that was sent. Routers. Routers actually route those packages, those packets. So you can see that in this example, if we're sending information and there's a possible destination of 3 computers that we can send to, when we send a request, that request can go to any of these routers in the network. And there are technologies out there that actually determine the fastest route, the best, most efficient route for your request to travel through a network. And so in this case, the most efficient route to get to, if your destination is the second computer here, see that the technology decides that this is the fastest route. Your request knows the address of where it needs to go. This is the address. An address could be something like google.com. Essentially, you could also create a request to go to computer 1 over here. And once you submit that transmission, that message, you may get a completely different route. You may see that your message follows this path instead. Domain name server, DNS. We saw this in Kahoot. We saw the question, what is DNS? And DNS is essentially the phone book of the internet. Domain names are our names for different destinations. An example of a domain is Google. An example of a domain is Clarusway. And so your DNS knows that for the destination google.com or clarusway.com, it knows what the address is for that destination. And so DNS actually is the phone book that stores all of that identifying information. We use for the internet what's known as a URL, or a Uniform Resource Locator. We just talked about domains here. This prefix here, World Wide Web, that is known as a subdomain. And then at the end here, this is known as a top-level domain. HTTP, in this case, HTTPS, that was the protocol, the combination of rules, procedures that we can use to actually reach different domains. We also have what's known as root DNS. So we have all these phone books, all these addresses, and how that technology is organized is we have a grouping of authoritative name servers that serve as the DNS root zone. We call that root servers. And there are a network of hundreds of servers all around the world, and they are configured to define the DNS roots of the network. And there are 13 authorities around the world that actually do that. So that root DNS server knows what we mean when we are visiting a website that is a .com website. So a phone book of .com addresses, google.com. The root DNS server knows what we mean when we're trying to reach an address as a .org DNS server. And then also it knows what type of DNS names we have if we're trying to reach an educational server. So typically in the history of all these suffixes in our URL, .com was commercial, org were kind of your nonprofit types of organizations, and then edu, that's going to be your educational facilities, things like that. So two examples of addresses that would be stored in this DNS server for .coms, yahoo.com, amazon.com. Whereas in org, you would see something like PBS, the Public Broadcasting System.org, that nonprofit destination. And then in our edu DNS server library, we would have the IP addresses for what poly.edu stands for, or what umass.edu stands for. And you can see the flow of requests and reply that the computer has to follow to actually find our destination site here, which is Google. So our computer first makes a request to our DNS resolver. All right, so we've provided that address to this resolver, which the resolver knows to go to the root NS, the root DNS server. It says, okay, where do I find this google.com? The root NS server knows where that information is stored. It sends that information back to the DNS resolver. And you can see that we have a request out to the TNS server. That comes back to the DNS resolver. Finally, the DNS resolver reaches out to the Google DNS server. Google says, all right, well, the location that you're trying to reach for Google is located here. Sends that back to the DNS resolver, which sends that information back to the original computer, which allows that computer to connect to the Google web server. LAN and WAN, local area network is what we're talking about when we talk about LAN. And that is a smaller network. It can be your home network, which could be a collection of computers, tablets, smartphones, all on that router that you use. Say you use a cable router. That cable router connects you over to the internet. So that's their local area network. Whereas your wide area network, that is a collection of different local networks. So your local network goes through the wide area network, say, to the network of your company, and you go through and through a gateway that allows you into that collection of servers or computers. And what I want to do now is kind of show you, this is known as a trace, what happens when we try to go through and find a connection to, well, for this one, we'll use google.com. I'm going to put the link to this in Slack. I can never remember what Slack is. Slack is Slack. So this tool is known as traceroute. And the way it works is I want to see when my computer requests the domain google.com. I'm going to type that in there. What actually happens? What are all the exchanges, like we just saw, of information that goes through the internet? Where's my information sent? You can see here, it's telling me it's sending the packets. So that request. What happens is my request goes through this Linode-AP, which the company is Linode LLC. It's in the US. It took 0.5 millisecond. And then this is the host name of the computer that it went through. Then it went to Google, took 2 milliseconds. It found these hosts, so these IPs. And then of course it came back to me. And these are the components of that request. So my IP address went out to this server, and this is a cloud computing company. So it's hosting, destinations on its cloud system. And a cloud is just a virtual collection of software, of web pages, all kinds of data. Then it handles through the following different servers. So all of these different servers are bouncing around my request, trying to resolve the request. Finally, it returns the address that I need to go to this guy. This guy then says, all right, that Google information that I need is located here. And then Google says, all right, well, specifically, they're looking for our homepage. So Google may handle my request specifically through these different machines to finally say, all right, that web page that they're looking for, this is the IP of that web page. And then that information needs to get sent back to me so it can resolve that that page. It can send that information back to me in packets. And I'm down here in Florida. You can see that my request going through all these different servers. So it had to bounce through boom, 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 and all the way back, boom, 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 from Florida all the way up to this Linode company way up here. It looks like they're in New York. So when you're making that request and getting that response, you're hitting servers all over the country. And it is that dynamic routing system that helps us to find our next, next node, next point in the connection, so that we can get to and find out the address of what we need to access, what we're requesting, and sends that information all the way back to us. And that didn't take very long. I think it took a lot longer because of this tool that I'm using where it's logging all of those connection points. But in reality, when I go to google.com, you can see how fast that was. I'm just right there. Oh, somebody was in Canada. It went through Linode too. So maybe invest in Linode because they seem to be handling a lot of network traffic. When we connect, say you go and you are in other places around the globe, when you need to access the server in, we'll say another continent, we'll say that's a good example. It may not be another continent, but you just have to travel to another area of your own country. You can see all of these little faint connections here. These are all undersea cables that allow us to connect from, in this instance, it's Australia all the way over to Africa, Middle East area there. Sometimes in the news, you will hear about efforts to lay undersea cable. It's pretty expensive. You will hear about environmental weather systems that may threaten undersea cables. And the significance of that really is huge, because that is how we are connecting through business, through personal connections over the internet. You can see within Asia here, there's a whole bunch of connections that possibly are in the same landmass, connecting that landmass back to itself. But the routing through undersea cables is probably faster than trying to build routing overland. And that's why you see undersea cables utilized there. All right, that was just a kind of a visual of where all of these undersea cables run through. I was looking through Zoom and Slack, I saw a question. And one question was, do they have different types of TCP? Yes. So TCP IP protocol examples, some of what we talked about. There's DNS, FTP. So there's HTTP, which that's going to be your hypertext protocol. But FTP is your file transfer protocol. So when you are transferring files between servers, you use a protocol called FTP. There's different types of TCP protocols for transporting of data, transporting of application or presentation layer information. So different types of data that you send, they can use different types of protocol. And of course, that is to interpret the data and I guess really to interpret the data properly and more efficiently. And then I see a follow-up of private IPs. You see that in homes, right? Yes, because your private IP is going through that cable server, and then that cable router is sending you to the cable provider servers, and the cable provider servers actually have that public IP that the rest of the internet can see. And there's some security that is provided with that setup, because if the whole internet could see your IP address, your private IP address, you might get a lot of requests, and some of those requests are not always benevolent. They could be service attacks on your specific computer. And so in between your private IP address and that public IP address that you're using to access the internet, there are security measures in place to prevent malicious attacks on your system, on your computer. And then there's a question about, what does destination mean? And destination is essentially where you're requesting the information from. So that destination server is when I try to access Google, the server that we saw here, the final server, that's the destination server. That's the destination of my request. Then I see some comments about the undersea cables. Yes, it is enormous. It is so impressive. And the fact that these cables are so narrow, 3 inches wide, to me, that sounds like they're incredibly fragile, but they endure. So the fact that they are comprised of fiber. So that fiber optic cable is tiny. Data can flow over that fiber optic system quickly. That's what allows us to actually transmit that request and get that response quickly, is that fiber optic component medium that all the data is sent through. All right, so now I'm going to have you tell me through Pear Deck, what are these things? What is the internet to you based on what we talked about? What is an IP address? What is that TCP IP transfer protocol? And what is DNS? BC said, what port is used to convert domain names to IP addresses? What do you mean port? That's going to be your DNS. So the DNS, the domain name server, that is what's going to do that conversion for you. I have a request in Zoom to show the slide of a URL again. So once we get through all these slides, I'll go ahead and I'll pop that back up, because we're nearing the end of our time together. I just want to get through a couple more things before we close up and go back to our daily routine. So yes, the answers to this are, IP, Internet Protocol, is a way to communicate. We have unique addresses. Domain names are like real addresses that you see on an envelope for the mail. And yes, TCP IP is a set of rules for computers to communicate. Perfect. I love it. I see internet is a huge network to connect to other computers and devices. Yes, it is. All right, so based on everything that we discussed, go ahead and Pear Deck and give me an idea of how you are feeling. Got one person that is incredibly happy. But tell me how you feel about the content, about some of the concepts. Some of the concepts are more confusing, more complicated, and that's okay. I don't work in the network technology segment of IT. So a lot of these things, a lot of these technologies, people dedicate their professional lives to, and they get very intricate. So if you have an interest, if you have a penchant for network technology, and that's kind of the direction you want to dedicate to studying, that's something you can do. If you have a penchant, you find software development incredibly interesting, then that may be an area that you decide to commit your professional development to. Obviously in IT, you have to know all of these things, because if you're working in software, you have to know how that software interacts with the network. You have to be able to talk to a network engineer, a CCIE engineer, that's right. You have to be able to talk the talk. You don't necessarily have to know how to fix everything when it breaks, but you do have to know how your technology works with other related technologies. So if you're in applications, somebody else may be in server support, somebody else may be in network support. You kind of have to know a little bit about everything. All right, Ollie, let's see. I don't think I'm seeing all the responses. I don't know why. Oh, there we go. I have to scroll through them. Whew, that one. Super, super. Thanks so much. All right, so let's close that shop up. Thank you very much. I'm going to circle back to that URL breakdown real quick for that request. Got a request. Somebody wants to know what I do for a living. I'm considered a systems analyst, specifically for Oracle ERP technology. And Oracle ERPs, they're offered through like a client server side setup. So we saw those terms discussed in our class, but also a cloud-based. So we don't host that technology on premise like we do in a client server side older technology setup. We actually have that client server side that server side is in the cloud, whereas in the past that server would be either at your work location or a server farm, which a server farm is just where a company will specialize in hosting servers and providing that hardware. Ikram, you have one more session with me. Yep, Sun Systems. Sun Systems does that. And so as a systems analyst, I have to know how my database interacts with a server, whether that database is hosted on I had a database that was on Solaris, which is Sun, was Sun, I think now it's Oracle bought Sun, but also we have a database now at my new organization on Linux, so a Linux operating system. In addition to having to be able to interact with that Linux operating system, which is text-based interface, not GUI or graphical user interface, I have to know how that server interacts with the network. So when trouble arises, I either know where to go to get an issue fixed, or I need to know how I can fix that myself. So there is our URL. Obviously, when we type out a URL or a web address, Nowadays, we just type out this domain and then the top level domain. Again, top level could be .com, .edu. Military is .mil. So if you're going to a military site, and .org is those nonprofit sites. It is common to have a domain that is the same domain name, but this top level domain may be different. So you may go to a website, say, I don't know if this is a real website, but say some computer. So somecomputer.com is a commercial domain where there may be a company called Some Computer that's a non-for-profit. So I've seen that before, where the domain is the same, but depending on this top level domain, it is two different companies, two different websites. He's asking for that trace tool. I'm gonna put that link in again. Go out there and search for a whole bunch of stuff. Now, if there are any questions based on what we learned, feel free to unmute, ask me now, put it in Slack, whatever you are comfortable doing. And always, if you have questions and you want to reach out to me directly, that's fine too. It is good, though, to publish your questions so that everybody can see them, because I guarantee you, if you have a question, somebody else has a similar question. So, all right. If you are ready, you don't have any questions, feel free to disconnect. I'm going to stay here for a few minutes just in case some questions pop up, and I will see you next week. Let me see, when is our next session? Wednesday the 19th, we'll be reconvening. So I will see you then. Thanks, Ikaram. I hope you have a great week. Until I see you again, until we get to speak again, enjoy.